This is the next video in the chapter on stoichiometry of chemical reactions. We are now on our third type of chemical reaction. We have done solubility, we have done acid-base, and now we are going to do redox, which is short for reduction and oxidation. So this is probably the type of reaction that you are least familiar with in terms of chemistry understanding. In this type of reaction, electrons are transferred from one substance to the other. And just like acid and base, it has two major parts. It has the reduction part and the oxidation part, and they always go together. If something is reduced, something else must be oxidized, because you can't give an electron to nothing. Something gives and something takes. And this includes a couple of types of reactions you may have heard of before in high school. So single displacement falls under this category. And combustion reaction also falls into this category. So where have you seen redox reactions in your real life? You see them all over the place. Basically, anytime you see a reaction happening with oxygen, you are seeing a redox equation. So anytime you burn fuel with oxygen, whether that is as a campfire, whether that is the gasoline in your car, whether that's the lighter that you use to light a cigarette, any of those burning of fuel and oxygen are example of reduction and oxidation. And anytime you see something rusting, like iron metal that makes up a building or your bicycle frame or your car, that reaction is a redox reaction with oxygen as well. So these are things that should be familiar. So here's an example of a redox equation. If we take zinc metal and we combine it in solution with dissolved copper 2, this will lead to copper solid precipitating out and zinc going into solution as an aqueous ion. So you may not immediately recognize this as a redox reaction because you haven't been trained to know what to look for. So what do you need to look for? We know that every redox reaction contains two halves, reduction and oxidation. And we can separate those specific parts of the reaction by writing a reduction half reaction and an oxidation half reaction. Just like we can separate an acid and a base out from each other in an acid-base reaction. So we can identify oxidation. Now I'm going to do that one first, down here. And then we'll look for reduction next. Okay, so what are we looking for? So our oxidation is going to be our zinc going to the zinc ion. So the unwritten part of the reaction in the full version is that this zinc solid is giving off electrons. It's giving off 2 electrons to become that ion. And that's the part that makes it reduction. So zinc loses electrons because we see them separated in the product, and that makes this oxidation. And so zinc is the thing that is being oxidized, and we have a special name for the reactant that is oxidized because when it's oxidized, it allows something else to be reduced. So we call it the reducing agent. It's a little bit confusing that the reducing agent is the one that is oxidized, but you can think of it as helping the reduction process. And so the thing that is being reduced is going to be the copper. That aqueous copper in solution is gaining 2 electrons to become copper solid. And the reactant that gains electrons is reduced. So I'm writing it in this weird way like this because there's an acronym that we use to help us remember. The acronym is LEO says GER, for loses electrons is oxidation and gains electrons is reduction. This is the easiest way to memorize which one is which while you're first learning. And so the copper ion, the copper 2+, that's the species that is being reduced. And by being reduced, it is helping to promote the oxidation half reaction. So it is called the oxidizing agent. It's named for the other half reaction that it helps to complete. So we have a little more information, right? I have now told you what's being oxidized and what's being reduced. But when we add these two together to get our total balanced reaction, you can see that the electrons aren't there. So if the only way to identify what's being reduced and oxidized is by finding the electrons, we are just going to be out of luck because they're not listed here. So there has to be another way to identify what is being oxidized or reduced, and that thing is called the oxidation number. So let's talk about that next. So we can identify which reactant is being oxidized and which is being reduced. Using what is called the oxidation numbers, or sometimes they're called oxidation states. Okay, we have kind of like squished that in here, but I'm going to fit it on this page, so hang tight. We're going to write over here now. So what is the oxidation number and how is it different than the other numbers that I learned to write on top of an atom? How is it different from the formal charge? How is it different from the ionic charge? We have a lot of different numbers like this now. So oxidation number represents the hypothetical charge of an atom if we assume that the bonding electrons are shared unequally. Okay, so electrons shared unequally. So if you think back to when we defined formal charge, for formal charge, we assumed that electrons were shared equally, that in every bond, one electron went to the atom on the left and one went to the atom on the right. When we do oxidation number, we assume unequal sharing. We assume that the more electronegative atom is going to take both electrons in that bond. So essentially what we're doing is we're pretending that every compound is an ionic compound, even though it isn't, even though covalent compounds definitely do not have a charge on each atom. We can pretend that they do have a charge and assign them this hypothetical number to help us decide what's being oxidized and what is being reduced. So there's a couple of numbers to help us decide, and I am going to provide you with these to help you assign oxidation numbers. And this is going to work the same way as the solubility rules, where there are going to be 7 sometimes conflicting rules. And if you have 2 rules that conflict, you break the rule closer to the bottom, you follow the rule closer to the top. So our first rule for oxidation number that is always, always, always true is if you have a free element, its oxidation state is 0. So that's true for like our zinc solid up here. If you have a compound with just one element in it, then that element's oxidation state has to be 0. Our second rule, which is always, always, always true, is the sum of all of the oxidation numbers for all of the atoms in a compound is equal to the charge of that compound. And this is the same as it was when we assigned ionic charge, right? If we have a compound with a charge like this copper 2+, the sum of all the atoms in the compound, the sum of all their oxidation numbers has to equal 2+. Okay, then we start to get down to specifics. So another rule that is always true, atoms from group 1, like sodium, always going to have an oxidation state of +1, just like their ionic charge. And atoms from group 2, like calcium, whoops, always going to have a charge of +2, just like their ionic charge. So from this point, everything is definitely true all of the time, and it's the same as we saw for ionic charge. And then we have some more rules that are most of the time true, but not always. And they match up with what we would predict from predicting the charge before. So rule 4, fluorine has an oxidation number of -1. Rule 5, hydrogen usually has an oxidation number of +1. Rule 6, oxygen usually has an oxidation state of -2. And rule 7, the halogens in group 17, those usually have an oxidation number of -1. So some of these rules at the bottom are frequently broken, but this is a good general guideline to help us decide. So in the little bit of space we've left ourselves over here, let's do a couple of examples. Okay, here's a molecule, sodium sulfate. Let's see if we can assign oxidation numbers to these. So the rules are pretty similar to predicting the charge in an ionic compound. Sodium, there's a rule for that one. That is always a +1. And oxygen, there's a rule for that one. That one is a -2. And then we don't have a rule for sulfur, so we're going to have to figure it out by process of elimination. Because we know according to group 2, the sum of all the oxidation numbers in the compound has to equal the charge, which is 0 for this. So I like to write the charge of each individual atom on the bottom. And if there's multiple atoms, I write that number on the top. So there are 2 sodiums. So the total of all the sodiums is +2. There are 4 oxygens, and the total of all of those is -8. The sum of the compound is 0, and I need a number for my sulfur. So if we take +2 minus 8, we see that the sulfur equals +6. So I will just write it down here with my individual atoms' oxidation states. So remember that if a problem wants to know what the oxidation state of a particular element is, it wants to know these numbers. It wants to know the oxidation state of just one atom of that element. I think we have room for one more. So here's an example of a compound where we cannot follow all of the rules that we are given. So hydrogen is usually +1 according to rule 5. Oxygen is usually -2 according to rule 6. But rule 2 says that the sum of all of the oxidation numbers has to equal the charge, which is 0. And +2 minus 4 does not equal 0. So we have to break one of the rules. So we will break rule 6 because it's closest to the bottom. So we'll have 1 hydrogen that totals to +2, which means our 2 oxygens have to be a total of -2, and each oxygen has an oxidation state of -1. So once in a while, we see exceptions to these rules, but they're a good general guideline and starting place. So let's return to our example redox reaction up here. So now that we know about oxidation numbers, we can indicate which of these is the oxidation and which is the reduction. The other definition for oxidation is you can tell a compound is being oxidized when the oxidation number increases. That's how we can identify oxidation. And so if we look at zinc, zinc is in a compound with a charge of 0, so the zinc has to have an oxidation state of 0. Zinc on the right side has a charge of +2. And so we are going from 0 to +2. So our oxidation number for zinc is increasing, and that's how we know it's oxidation. The opposite is true for reduction. In a reduction reaction, the oxidation number is reduced. That's what the reduce is referring to. It's not referring to the number of electrons, because the number of electrons is actually increasing. We are gaining electrons. Reduction is referring to the oxidation number. So copper is going from +2 to 0. So the oxidation number is getting smaller. It is being reduced. And so when we have a full balanced reaction like this, we will often label that to help us keep track of where the oxidation and where the reduction is. So we can write our oxidation numbers above each. And then I like to draw arrows to help me highlight which is the oxidation, half reaction, and which is the reduction, half reaction. So we assign the oxidation number, then we identify the oxidation and the reduction half reactions. And after we have done all of that, we will learn a new method of balancing reactions, especially for redox that takes those electrons into account, and those will be in the next video.